Hello everyone, this is Dr. Ross joining you from outer space. So I'm going to start sharing my screen and we'll get going with our introductory overview of Chapter 1 in our Chem 1A class this fall. So I am pulling up the PowerPoint slides that I posted to the class. Now, for the most part, these PowerPoint slides, let's see if this is going to, maybe we'll put it down there at the bottom. Okay, I don't know if these PowerPoint slides are going to be very obvious to everybody. So rather than just simply read the PowerPoint slides, and I trust that you don't need me to read to you, I'm going to try and add my perspective on some things as we go through to hopefully complement your own perspectives. So welcome to Chem 1A. This is the first of a 2-semester sequence of general chemistry designed for both science majors and non-science majors or students considering a field outside of science or what have you. For the most part, I intend to have asynchronous lectures. That means that I'll post videos like this one I'm pre-recording. The benefit of that is that students can have obligations in addition to showing up whenever I tell them to. So it's very flexible in terms of your schedule. The downside is you can't ask questions live, but a lot of students may or may not want to do that anyway. So you can always post your questions asynchronously too, right? You can post your questions to me through Canvas. You can shoot me an email, what have you. Okay. The only way other than Canvas to contact me if something is urgent is to email me. This is the way to contact me if something is private as well. So you can email me at jross36@ivc.edu. And just a quick mention to any student on the wait list. You know, as it says here, I am monitoring the wait list. I know that up until August 17th, I know that the class system, the management system, will automatically offer spaces on the wait list to students on the wait list. However, if those students don't act within I believe, a 24-hour period, it moves on. If you've already been moved past on the wait list, I believe you're automatically deleted off the wait list. If anyone is on the wait list, I'll follow it. If the wait list is exhausted and people show up, I'll definitely be sympathetic to petitions. Okay, so let's begin and see what can happen. Well, I guess that's a bad sign. I can't get the next slide up. So let's see. Oh, there we go. So just some reminders. Again, I'll have a separate video going through the syllabus. Please purchase your course materials as soon as you can. We're using Achieve, which is a Macmillan product for the lecture and the online homework. We're using a related product through Hayden McNeil for the lab. Instructions on how to access both of those are available on your syllabus. You really should only be using a Google Chrome browser. Not only is it preferred by all the software that we use, it's the only type of browser that will allow you to take the quizzes. So please just get in the habit of using Google Chrome. There are important checkup activities posted to Canvas. Please don't miss those deadlines. Specifically, when I go through on Monday, I'll have a Zoom lecture going through the first 2 check-in activities, just so that you can show that you're participating and I know that you're actually participating. Failure to hit those 2 initial deadlines would unfortunately result in removal from the class. They're allowing space for students that are actually knocking on the door trying to participate. So I'll go through those on Monday to make you very aware of those, Monday, August 17th. I don't provide study guides. So essentially show up, pay attention, do your job, and do all the homework, and that's your study guide. You know, I didn't know what a study guide was until I came to the US. Nobody ever, I think it's an invention over here. I'm not sure. And certainly as you advance through your career, fewer and fewer people would know what you meant when you said study guide. Pedagogically, I don't like it because it essentially says anything that's not on the study guide is not important. Only learn what's on the study guide, and that just doesn't cut it in reality. It's important that a student builds a sense of what's important for themselves, and that's definitely something I will try and model in this lecture I'm going to give now. But definitely a student that needs somebody to tell them what's important is a student destined for stunted growth. So I definitely don't want to encourage that in my class. Okay, so without further ado, the way the course is going to be set up, we're going to look at topics, not chapters. But because I appreciate that you're at home with a textbook, I'm going to highlight the chapters that support the topic. So the first topic is matter and the scientific method, and this will be supported by chapter 1. Okay, so again, I'm not just going to read through all these slides. That would be pretty redundant, I think. But what I will do, I'll try and give some perspective as we go through these slides. And I'll try and move this bar around. I don't know if you'll be able to see this bar when the recording comes up. I have my Zoom bar at the top there. So we're in a chemistry class. It's important that you know what chemistry is. So as shown here, chemistry is the study of composition, structures, and properties of matter. I would probably just say chemistry is the study of matter. That's probably where I would go. So chemistry is the study of matter, where matter is anything that occupies space and has mass. So if you think about it, what doesn't occupy space and have mass? Everything, right? So in medical applications, if you're a physician or a nurse in some discipline and you're studying a patient, well, your patient has mass, they occupy space, that they're on the table or in the bed. So your patient is matter, so you're a chemist. A civil engineer or any type of engineer, the project that you're engineering towards has mass, occupies space, so you're a chemist. So chemistry, therefore, because it's so broad, it's actually a pretty useless title because it essentially is everything. Matter can undergo changes in mass caused by changes in energy. We're not going to talk about energy that much today. Energy is very challenging to talk about, as we'll see when we eventually get to it. I would add something here where it says energy is the capacity to do work. I would add, I would go back and I would add, and transfer heat. So heat is a type of energy we won't talk about today, but it's that work and heat, which are very different, as we'll see later in our course, that we predominantly associate with energy for the most part in Chem 1A. And I would associate that with this definition. Okay. So what we're doing here is we're classifying matter. So we can classify the matter, and I would definitely encourage you to read these slides. But what I would like my students to think while they're looking at this elementary stuff is, why is it recommended? Why do the people that wrote this book recommend that I start this way? What's the benefit? What am I doing in chapter 1? I'm looking at some definitions. I'm looking at some vocab, and that's important. Chemistry is definitely a language. and you have to speak the language to understand the concepts. But why am I characterizing matter? Because in any problem, you have to characterize the pieces of the problem, right? So for example, let's say you're doing an old picture puzzle. You open the box, you might tip all the pieces out, and you might start to categorize, okay, this, let's say it's a picture of a forest with an animal in the center of the picture. The animal's brown and the forest is green. You might start to look for all the brown pieces and you put those in the center of a big board, and you might get the green pieces that you can clearly see represent the canopy of this forest, and you put those on the periphery of the board. That's because it makes future jobs easier. Ill-defined future tasks, like actually piecing together those brown pieces to make up the animal and piecing together those green pieces to make up the canopy, it just makes that future job easier. That's essentially what we're doing in chapter 1. We're looking at the layout of the land, who are the players on the scene to some extent. We do that for the first few chapters. But in chapter 1, we're just essentially learning what we're going to need to do moving forward. So it's crucial, although chapter 1, you might look at it at first glance and think, ugh, I did that in high school, or I didn't do it in high school, but it looks simple enough, I'm not going to worry about it. I would say that's ill-advised. I would definitely refer back to chapter 1 frequently throughout the class. That would be my recommendation. So chapter 1, I know is going to repeat, these slides I'm looking at now, I'm going to glance through them because I want to get to this diagram, which kind of summarizes everything. So this is the classification of compounds. And again, I made these slides available to you so my students can download them and annotate them as they see fit. So chemistry studies matter. So we've got matter at the top here. Up here. Matter, anything that has mass and occupies space. That's a very broad category. So let's try and refine that category. We've got pure and mixture. Let's look at pure for a second. So pure is essentially one type of matter. So one type. Now again, type is broad. So although we're becoming less general, we've added the general word type. Now we'll specify what we mean by type with two broad categories. So let's say an element is a type and a compound is a type. So we've subcategorized these two types. An element is anything that's in the periodic table. So there's 118 elements in the periodic table. And in my assessments, and to be honest, any sane person on planet Earth, if they assess their students, they would furnish them with a periodic table. I think anyone that tells you to memorize a periodic table has pain in their heart and darkness in their soul, something like that. I don't know. There's no need for it. Anyway, so you just look at the periodic table. If you see any of the 118 elements there, you know it's pure. A compound is two or more different types of elements. So a compound is two or more different elements combined to give a unique substance. So for example, water here, you've got an ice cube. So we've got an example here, H2O. This means we have two elements, hydrogen and oxygen, or two types of elements rather. We have three total, two hydrogen and one oxygen. But we have two types and they're combined together to give one unit of water. So that would be a pure compound, although it's a mixture of elements. The elements are not free to unmix anymore. Okay, so that takes care of the pure branch. The mixture branch, there's basically two types of mixture, homogeneous and heterogeneous. The prefix here, homo, means same. And essentially it looks the same. Looks the same to the unaided human eye. And hetero means different. So it looks different to the unaided human eye. Okay. I was going to time this video and I've just realized I never started my timer. So I'm going to guess how long I've been yapping on for. And I will arbitrarily assume I've been yapping for 20 minutes. Okay. So who knows? Maybe I've been yapping for 2 hours and I just don't know. So here's a couple of examples here. So this salad dressing, why is it heterogeneous? Well, clearly there's more than one type of thing here. There's clearly what looks like oil here. There might be some spices down here. Looks like maybe some chili or some pepper seeds or what have you. Oh, some spices. And I can see that they look different. I can see the spice bit looks different. I can see a clear oil layer. That doesn't look like it's the same to me. But I know it's more than one thing, so it's a heterogeneous mixture. And heterogeneous mixtures can be separated. You could decant all the oil away, or you could filter, put it through like some kind of filtering material, a mesh, for example, and you could filter away all those solid and particular pieces. On the other hand, it's a pretty poor diagram here because they've just shown the label. But if you imagine vinegar, so you'd have to use your imagination here. So why have a picture of you if you're then asked to use your imagination? But if you imagine vinegar, there's no lumps in it, there's no bumps in it, there's no particulate matter in it. It all looks the same, but we know that vinegar is actually a mixture of water and it's got acetic acid in, which is not the same as water. And it might have some preservatives in, it might have a flavoring in, it might have other things in, but it's more than one thing, but it all looks the same. So that would be a homogeneous mixture. Can you separate homogeneous mixtures even though there's nothing to see that's different? Yes. It's a bit more tricky on occasion. You'd have to use differences in physical properties. So for example, if you had salt water, which is a mixture of salt, sodium chloride and water, all looks the same. How would you separate that? Well, you could boil the water away and reclaim the salt and the water separately. So you can, importantly, you can separate mixtures. Definitely important to, given samples of matter, be able to categorize them this way. Okay, visual representation is also important. So I've never really understood why. Chemistry learning theory says that students often have a hard time showing what they know when you present them with visuals like this. And I don't get it. I don't see why. But statistically, you'll be predisposed to mess this up. So let's make sure we break the statistic. If you're given diagrams like this, look at what you have. Look at the definitions that you know from the previous page and look at what you have. So these are atoms of helium, but who cares? They're atoms, period. Atoms are essentially elements, but elements are flavors of atoms. So there are atoms, but there are 118 flavors, unique flavors called elements. I can only see one object here, and it looks identical to this one, looks identical to this one, looks identical to this one. These look like elements. I only see one type, so it's pure. If we look here, this specifically is carbon dioxide. So the black sphere here is carbon, and the two red spheres here are oxygen, but it's all one unit. It's one chunk, and that one chunk repeats over here, and again, and again. So I've got a CO2 up here, a CO2 down here, another CO2, you guessed it, no surprise, CO2. Now CO2 is a mixture of elements, but they combine in a way that they're no longer able to separate. It's one structure, and that structure, that one structure then repeats. So it's a compound, it's two or more types of elements combined, but it's one unique now piece of matter. So again, it's still pure. Here, we're told we have a mixture of gases. So these white spheres are hydrogen. So this is just a hydrogen molecule, H2. Here's another one, H2. Here's another one, H2. This blue one is nitrogen. So we've got an N2 molecule, an N2, N2, etc. And the red one is oxygen. So we've got an O2, an O2, an O2. So we've got a mixture of H2, O2, and N2. We've got a mixture of diatomic molecules. They're all different. Now, can you see oxygen? You know, all of these gases are present in the air in front of your face. So the air in front, well, actually, there's no air in space. But imagine I wasn't really in space. Imagine I had air in front of my face. So if I look at the air in front of my face, I don't see oxygen, hydrogen, and nitrogen, but it's there. So because it looks the same, it's a homogeneous mixture, but certainly a mixture. I can find where my, oh, it's over there. Anyway, so this type of representation is known to plague students, but hopefully will be the exception to the rule. More. So actually, I have a printout of the slides here, so I can see if there's anything I want to glance over. Again, because I want to avoid reading them to you like story time with Dr. Ross, but I definitely encourage you to read them. I just want to see if I can add any words of wisdom that might actually benefit you. The next slide looks like something we should pause on. Okay, let's see if I can offer any insights here or viewpoints. Chemical reactions. So this is the transformation of matter from one form to another. So remember we said matter is anything that has mass and occupies space. Chemistry is the study of matter and its changes, which are caused by energy changes or transfer of heat changes. Here's a typical chemical reaction layout. We will be looking at chemical reactions later on in our course though. So let's look at this basic overview. This is the synthesis of water. So we have hydrogen here, which we saw the two white spheres are H2. We have oxygen, which we saw is O2. And we have H2O. So HOH. Okay. This is visually what the model looks like. And we have energy as well. Why is there energy? Well, the hydrogen and oxygen are going to come together. And just as when anything comes together, my hands or two objects, they come together. And that release of energy that you could hear on this occasion, it's not always sound energy, but it would be thermal energy in this case. But it would be the liberation of energy. On the left of this arrow represents change in time. So initially we have two materials. You wait for a change in time and eventually you have a single material, but energy as well. Importantly, if we look at the mass plus the energy here, that must equal the mass plus the energy here. Now, it's harder to weigh energy. In fact, it's impossible to weigh energy because energy doesn't have a mass. So it's a lot easier to measure. So let's see, I want to avoid percentages here. I'm just going to say this mass and energy is easier to measure. This mass and energy is harder to measure. Hopefully you agree, because the energy component is larger. This fact will come up a bit later, I believe in chapter 2, when we look at Antoine Lavoisier's conservation of mass law. Keep this in mind though, but this is the type of thing that a chemist would do, look at this transformation. And it's the fact that over time, it's harder to measure the mass and energy. That was one of arguably the biggest impediment to the onset of chemistry and why it took so long for chemistry to get going. Chemistry is a very recent discipline, and that right there is arguably the main reason for it. So this is what chemists do. So welcome to the club. This is what you're going to be doing. So not only do we want to look at the change in time, we want to look at we want to classify the initial and final conditions. So you're going to see themes in chemistry. One theme is looking at change. One theme is looking at static, initial conditions. What do I have before any change happens? So we're going to look at the mass of molecules. We're going to look at the energy of molecules. We're going to look at the mass of products, the energy of products. Ooh, how does the mixing of oxygen with hydrogen change hydrogen? How does the mixing of oxygen and hydrogen change oxygen? That's the type of thing we're going to look at. Oxygen, when it's with one of its own kind, behaves in a certain way. Oxygen, when it's sandwiched between the hydrogen brothers, how does that behave? That's the type of thing we're going to be looking at. So that would be a heads up on that. So I'm just going to skip through again. My timer says I've got about 30 minutes, so if I can do that in less, all the better. Let's immediately go to constant composition. Okay, the law of constant composition is important. Now, if you were to Google this, it's typically known as another name. I think constant composition is a much more recent way to think about this. It's the old way to think of it, and I think the better way to think of it, if I can find my cursor, is Joseph Proust's law of definite proportions. Joseph Proust was, I believe he was French. He was the scientist that observed this. So I would learn the name. I would just call it the Joseph Proust law of definite proportion, but bear in mind that some people will call it constant composition. And essentially what it means, what's a definite proportion? Definite means exact, and proportion means ratio. So chemicals exist in exact ratios. That's essentially what it means. So for example, hydrogen, the molecule hydrogen, is a one-to-one ratio of hydrogen. Oxygen is a one-to-one ratio of oxygen. Always. So here, if you look at these two molecules of hydrogen, it's in a one-to-one ratio here, it's in a one-to-one ratio here. It's always in a one-to-one ratio if it's called hydrogen. If it's in another ratio, it's not called hydrogen anymore. So that's what he realized, and that knowledge, it seems possibly trivial now with the benefit of hindsight. But at the time, when people were figuring out what the world was made of, This was revolutionary. So it's definitely something I want you to be aware of. You can definitely be, it's reasonable to expect to be asked, which of the following can exemplify constant composition? What is the constant composition of the following? That type of question. So please keep that in mind. So let's see here. Law of constant composition. Yeah, so essentially, this is almost the reverse of what modern hydrogen fuel cells do, right? So a modern hydrogen fuel cell car would take somehow, whether a liquid source or a solid source that was converted to a liquid, has to have a source of hydrogen molecules. And then you would have oxygen from the environment, and you combine them together to make water. So actually, if I flick back real quick, this is what we saw here, right? So maybe I should actually annotate that. And this is, for example, a hydrogen fuel cell chemistry in a way. Well, essentially without the details of how the fuel, of how the engine might work. Chemical reaction. So hydrogen fuel cell, there's many types of them on the market now. And the energy here obviously would be harnessed to rotate the drive shaft and turn the wheels and get you to your chem class on time. Okay. This is the reverse. This is how you might make the fuel to begin with. So you can take water and add that energy back again. So whereas we said, let's make sure I'm not duplicating the next slide. No, I'm not. So whereas we said you could take hydrogen, this was what was on the previous slide, right? So we take 2 lots of hydrogen and 1 lot of oxygen, and we make 2 lots of water and energy. If we want to go back again, so to reverse, you have to put back the energy. So you'd have to take the energy, put it back into the water to make hydrogen and oxygen again, right? But you can't just, if you had a hydrogen fuel cell car, that energy would be lost as heat in the engine, maybe noise. I've never really gotten close to one of these things. I'm not sure how loud they are, but I'm sure they're not silent. Certainly not with moving parts. So the sound energy, vibrational energy, heat energy, all this energy is lost, and it's lost forever. So you can't use the original energy that came out. You can't like bag it up and put it back in again. You'd have to find a fresh source of energy, and that can come from a battery, as in this example. You could hook up a battery, and you can actually do this at home. You get a 9-volt battery, one of those square ones that you have in a smoke detector, a 9-volt battery, and you dip it in water, you'll see it bubble. If you want to do something more controlled, you could connect a wire and dip the 2 wires into 2 separate chambers of water. So you could have, the separate reactions going on. But essentially, this is how you would do it. Now, it's a bit subtle in this diagram, but look at the ratio here. Now, this is not the constant composition ratio. The constant composition ratio, so I want to make this clear. There's 2 different types of ratio going on here. If we look at this ratio here, if we look at a water molecule, look at a water molecule, the hydrogen to oxygen is in a 2-to-1 ratio. in water, the oxygen ratio here is 1:1, so let's not bother with that. But then you've got this ratio over here. So the rate, if you take a molecule and you look at the internal ratio of elements within that molecule, that's constant composition. Let's look at the ratio of molecules, though, which is totally different. So look at this line here and look at this line here. So if we look at this volume, let's say that the distance traveled here represents the volume compared to this distance traveled here. It's roughly in a ratio 2:1, right? It's roughly twice as, this tube went twice as far down. So we've got hydrogen, H2, twice the volume as oxygen. And that ratio is in this equation here. So this ratio here of 2:1, that's what, or here 2:1, the same thing in reverse, that's what's being recovered here in the volume. For every 1 molecule of oxygen, you produce 2 molecules of hydrogen. And for reasons that we'll see later in our course, that would have, these have the same volume. So if you have twice as many of them, it has twice the volume. Crucially though, that's not constant composition, that's not definite proportion. Definite proportion is within a molecule looking at the ratio of elements. Okay, I think I've beaten that one to death. So let me see if I can find anything else that I would point out to you. Maybe this slide. Yeah, I think these next 2 slides we might comment on briefly. Again, more vocab, cations and anions. Cations and anions. Again, without borrowing material from any of the chapter, which is hard, it's definitely challenging when you start chemistry because you can't, it's the best way to learn chemistry is slowly and in little bits. But to explain any one thing, you need a whole host of other things that you're not really supposed to mention yet. So definitely becomes awkward at the very first time you look. But as more and more things become allowed, everything else becomes easier to explain. For now, ions just means a charged object. And those ions can come in 2 flavors, positively charged and negatively charged. And these are the cations, and these are the anions. Okay, so just be aware of that. You can have monatomic or diatomic. Monatomic, which means 1 atom. Or you can have polyatomic, which just means many atoms. Okay, so here these 2 are monatomic because calcium is an element. Here it's got a charge on it, but it's still 1 element or 1 atom, so it's monatomic. Sodium likewise, both cations because they have charges. Don't worry about the fact that you've got a 2 charge and a 1 charge for now. We're not there yet, so we probably shouldn't mention it. But it's positive, it's 1 atom, it's a cation. Negative, these are anions because they have negative charges. But here, despite it has 2 symbols, Cl, sorry, not 2 symbols, it's 1 symbol, 2 letters. Elements always have a capital letter to begin with. So if ever you have a capital letter and then a lowercase letter, it's 1 symbol. If it were, so for example, chlorine here has a capital C and a lowercase l. The fact that it's a lowercase l, I know that that l is part of the C, so the whole thing is 1 element. So it's monatomic. Here I've got a capital O and a capital H. Two letters, but it must be two separate elements because they're two capital letters. So this is polyatomic. So you've got a polyatomic anion, monatomic anion. They both have two letters, but again, elements always start with a capital letter. Some of them only have one symbol. Actually, we haven't seen one here with one symbol. I guess they all had two symbols. But there are many, many elements with just one symbol, like carbon, for example, is just capital C. Oxygen is capital O. Here, the ones we were given had two. But be on the lookout for polyatomic versus monatomic. That would be something I would stress at this stage. Representation of chemical formulas. So I'm going to move my screenshot because I can see myself and I was right over my visual. One of the challenges you'll find in chemistry is the zooming in and out of different representations. So sometimes we say words, there's a lot of language. Sometimes we write formulas in chemistry. Sometimes we draw funny pictures and caricatures like this that have different meanings. All of these representations make it a little bit harder to know that we're talking about the same thing, but it's something you have to master. So structural formulas here. So these chemicals are all ethanol. They all, so with this COVID-19 pandemic, ethanol is the chemical that's in your hand sanitizer. It has to be about 60 to 70%. So that's how most of us would know ethanol. It's also the chemical in recreational drinking alcohol. But fewer of us would have access to that. Almost everyone has access to hand sanitizer right now, for better or worse. So ethanol, if you just lay everything out on the blackboard, you can see that it has 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. I'm looking up here now. So this would be the structural formula. Now here we're looking at the structure. This has got nothing to do with the shape. So one of the biggest things you'll realize later in this course, but certainly not in this lecture, is oftentimes in a textbook we talk about structural formula, but it's got nothing to do with shape. This is not a right angle between, this angle is not a right angle by any means. The angle between carbon, oxygen, and hydrogen up here is not 180 degrees by any means. This is just the way we write it down in a structural formula. In this ball and stick model, which in a face-to-face lab, we'd probably have a lab where you make molecular models. In this online version, because of the COVID pandemic, we won't be doing that. But here you can see it's much more realistic about the shape. And you learn to recognize color coding. So black here is carbon, white is hydrogen, red is oxygen. So you can see it's not 180 degree bond angle. And here you can see it's not 90 degree bond angle. And on occasion, for the most part, that's what we would look like. That's what we would look at. And then you have, so this is a lot more faithful to the shape. And then space filling, a lot more faithful to the shape, but it's more difficult to see. So I'm going to say shape easier, shape harder, because we've contracted, or rather in the ball and stick model, we exaggerate the separation between molecules, between atoms in the molecule. And in the space filling model, it's much more realistic, but it's hard to see the details inside, but we would see something like that. Okay, so these different ways to represent, and there's more besides this, but this will definitely be useful for us starting right now. There's not too much more. Actually, there's a few more things. Let's see if I can, again, look ahead at these slides to see if there's something I can maybe add some Yeah, I'm going to jump right ahead to this slide. Again, you would look at all the detail in between. I'm going to look at this. I'm going to move my image out the way. Okay, so these slides, everyone loves a good acronym. You know, I'm no different. I don't necessarily condone COAST. I've never heard of COAST before, to be honest. I think every textbook has its own acronym. We will be talking about problem-solving techniques. So if you want something to hold on to, here's one out of the box. So COAST is an acronym here for collect and organize, analyze, solve, and then think about it. So to map this onto an assessment, for example, which is not the most important thing you'll do, but let's say that you're doing an assessment that you're worried about. You've got a question, you would read the question and you would list what you have. You know, what do I have to play with in this question? That could be collect and organize. Then you could analyze, okay, based on what I know I have and what I know all my studying is telling me, what should I do next? Or what would be a reasonable thing to do if I'm not sure what to do? And then you actually perform a calculation, or you put your thinking in order, you brainstorm and come up with a logical progression that could all be solving. And then you sit back and you think, okay, I'm freaking out. I'm in an exam. Does what I've done make any sense whatsoever? You know, am I just going because I'm nervous in my exam? Or am I actually thinking like I did when I was practicing? So it's definitely important that you don't forget to do that. So this is reasonable. You know, just good problem solving skills. So this kind of fleshes it out a bit. Let's see what else I have here. Yes, this next one I'll look at real quick. Intensive and extensive properties. These are important. So again, chapter 1, remember, we're trying to think about ways to approach chemistry. So we're not learning a lot of chemistry yet, but we're getting our ducks in order. We're kind of prepping. You know, to use an ancient Roman analogy, you're a gladiator about to go out into the arena, but you're inside the tunnel. You can hear the crowd shouting. The arena is Chem 1A or chemistry, or what have you. And you're thinking to yourself, okay, what am I going to do when that door opens? I'm going to run away from the lion. That's what I'm going to do. So you're trying to get your strategy in order. That's what we're doing here. That's what chapter 1 is all about. So keep that in mind. And what I'm trying to do right now is to point out things that I want to really emphasize to you, so that if you're in that tunnel waiting to run out into the stadium, I'm saying to you, oh, did you tie your shoelaces? Make sure they're tight, because that lion won't wait for you to tie your shoelaces when it runs after you. And you know, I've heard that if you run right, it's easier than if you're in left. I'm trying to, because I know what's ahead of you. I'm trying to, in as short a time as possible, pinpoint things that I want to draw your attention to, and this is one of them. So intensive and extensive properties. One of them is more valuable than the other, and you can probably guess that the top one is more valuable. An intensive property is independent of sample size. So if you want to study an object, take a sample of it, and you can learn all about it if what you are learning about is an intensive property. You don't need a large sample. Let's say in a lab, you all take a different sample size. If you've been asked to study an intensive property, it won't matter. You should all return the same value. If you're going to study an extensive property and you all take a different sample size, you should all get different values. And then when you recombine to share experiences, you all think each other blew it because you all come up with a different answer. So that's less valuable. It's important that you know an intensive property when you have it, and it's important that you know an extensive property when you have it. So these examples here, color, you know, if you take a tin of paint that's well mixed and you dip your brush in it and you paint it on the wall, and then 5 seconds later you dip your brush in again and paint it on the wall, those two colors should be the same as if you splashed half the tin of paint on the wall. Luster just means shininess. Melting point, the melting point of one snowball outside should be the same as the melting point of the other snowball that you didn't sample. So you can assume that what you did sample represents the whole. Obviously, on the flip side, extensive properties exactly depend on sample size. So the mass, obviously, the mass of an object depends on how much you sample, right? If I sampled a gram, the mass of a gram is a gram. If I sample 3 grams, the mass of a 3 gram sample is 3 grams. 1 gram and 3 gram are not the same, so it matters. How can we spot intensive and extensive properties? Ratios. So density is an intensive property. It's one of the important ones. Density is an intensive property because it's a ratio. So if you scale a ratio, so for example, density is an intensive property. If you scale it, let's say I double the mass, well, that's going to double the volume. So it returns the same D, because essentially you just multiply and divide them by the scale. So you can spot an intensive property because intensive properties always have units on the numerator and denominator. So intensive properties let's say it's x over y, where x has units and y has units. An extensive property is going to be x over 1, where only the numerator has units, or 1 over x, where only the denominator has units. So mass and volume are just mass units divided by the number 1. So crucially, you have to have units on both the numerator and denominator so that when you scale the thing that has the units. So with an extensive property, you're only scaling the numerator or the denominator, but with an intensive property, you're scaling both. Okay, I hope I'm recording this video. I'm not sure now. Okay, there's a nice simulation here that you can go to, so that's good. Let's see how we're doing with time. Yeah, so I won't read. I kind of have to stop here because it's that important. Antoine Lavoisier, or maybe I'll just give you an assignment on this, I'm not sure yet. The law of conservation of mass was very hard to establish. So this was very challenging for the pioneers to establish, because you can actually have mass lost as energy. And it's very difficult to keep account of the mass of the energy that you lose. Very difficult to keep track of. This really, in my opinion, as far as I know, is why it took chemistry so long to get going. Chemistry really is only a couple of hundred years old. And it was when Antoine Lavoisier established through very careful measurements that, you know, if you look at the mass here, the mass and everything that's associated with the initial condition, and then at the end, when you've sealed everything, nothing can escape, you really don't see a change. who's able to see that there must be a conservation of this property mass here. So there's something fundamental about mass, and therefore it's worth studying mass, right? That's what was really hard, keeping a track of all that, of the different ways you can lose mass. You know, imagine you've got a piece of wood. You know, imagine you have a log. So logs of wood. And then you heat them, so you burn them. And then you get a pile of ash plus energy that you might have used to heat food or keep yourself warm or what have you. Essentially, the only way to measure the mass of all this energy is to trap this in a box. So you've closed essentially a box that contains all of this so that nothing goes in, nothing comes out. And that's really dangerous to do. But essentially that's what Lavoisier was able to do. So everything, nothing could escape, and he could painfully keep track of everything. So very important. This is what led to the birth of chemistry, and as far as I can tell. So that's important. What I would like you to keep in mind as you start to look at states of matter, this vocab, yeah, I mean, you learn some of this vocab in 3rd grade. That's not what's important here. What I want the emphasis for you to be in general chemistry is when you see a phase of matter, or you think about a phase of matter or a state of matter, state and phase mean the same thing. Think about what the molecules look like. So for example, here we've got a water molecule. You know, you've got the red oxygen here and the 2 white hydrogens here. And in a solid, they might be arranged in a regular array. Don't really want to talk about the shape today, so I'm kind of ignoring some shape discussions, but let's say it's arranged very, very orderly. Now, the reason why to the uninitiated eye, it might not look orderly here is because of the shape, but what you should see here is the proximity of red oxygens and white hydrogens. So like I've got here, if I were to do a similar shading in my diagram, my red oxygen, my red oxygen, my red oxygen. To bring the order out of the diagram, you can see that there's red oxygen and white hydrogen, red oxygen, white hydrogen, red oxygen, white hydrogen, likewise red oxygen, white hydrogen, red oxygen, white hydrogen, etc. Okay. Now it's not easy to see here, but in the liquid, if I were to simplify it in my diagram, it would just be a little bit more susceptible to variation because the liquid can move, right? So you might have slight alterations in the diagram. So you could have a molecule that spins around, and when you look at it, it just so happens that you see a white hydrogen there. It might spin back around again, but when I looked at it, it was a white hydrogen. So a bit more variety. That's what you want to think about when you hear the word liquid versus solid, or melting from a solid to a liquid. It's that visual that when you learn these vocab words initially in grade school, you wouldn't have. In college, when you start to see the same vocab words, that visual that makes the difference. There's some vocab that I'd want you to learn here. I'll add a little bit of vocab here. So melting, let's see, melting is also known as fusion. So you could have positive fusion It's hard to write. I'm actually writing uphill now, which is very challenging. You could have positive fusion that way. Therefore, freezing would be negative fusion. Oops. Negative fusion. So melting and freezing, arguably better way to think of it would be positive and negative fusion. Would I change anything else? Yeah, typically you have positive vaporization, and condensation, typically you would say negative vaporization. If I can write that, vaporization. This extra vocab I'm adding will become very relevant later in the course, not in chapter 1, but definitely later in the course. That was my alarm telling me I've been yapping on too long. But I'm recording this, so it matters a little bit less. There's a certain point. Yeah. Okay. A couple more things, won't be too much longer. And again, if you feel, that, I've got this material, then you can just look at the unannotated version, which I've made available to you. Okay, the scientific method. We're obliged to look at the scientific method, but the scientific method is loaded with controversy. So you definitely should know about it, and most people do, but by no means is that how everyone does science. And by no means am I going to talk about it ad nauseum right now, because I've actually given you a couple of assignments about it in week 1. So, for example, you are going to compare and contrast the scientific method with the inquiry wheel. A bit later on in our course, I'll ask you to compare the inquiry wheel and the scientific method with model-based inquiry. And then maybe a little bit later, I'll ask you to compare it with machine-based learning, which are all, none of which are the same as the scientific method, but which are all done by scientists. So definitely the scientific method, I would argue, sorry, it's uncomfortable in space. The scientific method, arguably, there are methods used by people to do science. So there are many, there are numerous methods used in science. So by no means is the canonical scientific method applicable to everything, and by no means is it the best. Although I don't want to say too much because of this assignment that you have. I don't want to say too much about laws and theories. I think that's pretty straightforward. Temperature conversions. This is a trivial thing, but something that becomes important when you can't do it. So it's important that we can convert between temperature scales in Chem 1A. So I would encourage you to memorize this one. Let's see. I would say memorize that one. I would say, or at least the way I do it, I would memorize those two. And then I would produce this one. So for example, if you've got degree F is 9/5, 9 divided by 5 is 1.8. Degree C plus 32. Okay. So let's say you've memorized that, but you want degree C. So we're going to produce the degree C one. Well, let's isolate it by taking 32 to the other side. So 1.8 degrees C is degree F minus 32. and then we divide both sides by 1.8. So degree C is degree F minus 32 divided by 1.8. And that's essentially what we have here. So there's 3 equations for the 3 units. There's 2 I would memorize, and there's 1 I would produce. Okay, and that comes to the end of the slides. That comes to the end of the slides that I have. Oh, luckily I was recording, thank goodness. I wasn't sure if I was recording this video. That comes to the end of the slides that I have for the first chapter. So again, I've made the PowerPoints available. I'll post these PowerPoint slides with my scribbles on, in addition, so you can have the clean version for your own scribbles, my version. I don't want to just read through them. If possible, I want to pick out features that, you know, might be important. I don't know if I've achieved that today. But just conceptually think about, you know, not just what am I doing in this chapter, but why am I doing it? Why am I looking at the scientific method? Why am I looking at extensive and intensive properties? How might that be relevant moving forward? What should I think about in chapter 2 from what I've just looked at in chapter 1? So that's what I want you to think about in the background as you start reading through. Essentially, what's just vocabulary in chapter 1, not much chemistry, if any at all. Chemistry really starts in chapter 2. So chapter 1's a great academic icebreaker, good way to, you know, just mentally get your head around what's going to happen to you. Okay, so I'll wrap it up there, conclude this video, and I will post the link for you to watch.